Okay, now let's continue. General Chemistry Part 21. At the end of Part 20, we finished the introduction of one type of chemical reaction called single displacement or single replacement reaction, right? Generalized as A plus BC become a B come out, A combined with a C become a new binary compound, right? And from the example we introduced, there are two examples. One is zinc in hydrochloric acid, and another one is the copper replaced the silver in the silver nitrate. Out of silver metal and copper combined with the nitrate become copper nitrate, right? And both cases they have a driving force we consider as a metal activity series, and then or called the reducing strengths of one compound, which is metal or elemental species, is able to replace the other cation out of the compound and then form a new product. Now, these two examples we introduced can also be classified otherwise as the first one because it has a hydrogen gas involved, and we call them a gas formation reaction. Or you have a solid, which is silver as a solid, silver metal, precipitate out of the solution. The copper get into the solution as copper 2 plus cation, and the aqueous solution become cation and anion, still the same nitrate. And then the solid formation is another classification for this kind of reaction. Both reactions have to be considered another type called the redox, because both reactions involve the electron transfer. Alright? The oxidation state for certain element in the reactants before and after of the reaction, for instance zinc, start with 0 as a solid metal, end up with a +2 cation in aqueous solution. There's 2 electrons lost to 2 hydrogen atoms in the hydrochloric acid to reduce hydrogen atom, cation into hydrogen diatomic gas molecules. So in those cases, electron transfers involved in both cases, we are classify them as redox as well. All right. So here we say also can be classified as, right? Now we finish that. Now the second type of chemical reaction is called the double replacement or double displacement. Now what is the chemical reaction? Defined as the cation component of one reactant. We have 2 reactants, right? 2 of them. Exchange its anionic partner with the other reactant to form what? Form new ionic compounds as solid or molecular compound as liquid. Alright? So that's the case. Now in general, we have a general format about the reaction. We use A, B, C, D representing the symbolic symbol for the elements in the periodic table. Simplify. And the AB is a binary compound. A is considered on the left as you write in chemical formula. Normally is a cation, and on the right is going to be B as anion. So for this particular purpose, I put the plus sign on the corner, left up corner for A and the right up corner for B, indicating they are cation, kind of cation and anion nature, right? For C and D, for another binary compound as another reactants, it will be the same. The C considered cation on the left and the right, and it's going to be could be a anion or polyatomic anion, right? But then the exchange partner for the anionic. So let's put it this way: we just put the B and the D will be switched the position. The D goes to A and the B goes to the C. But remember, the cation has to be always on the left. So you don't say A, B, and C, D, exchange partner become A, C, and B, D. Why you don't say that? Because the B is minus, D is minus, it's both negative. So you have to combine cation and anion to make a binary ionic compound, right? Otherwise there will be no compound because they both are negative charged, anion or cation positive charged. So in this case, we have to be very careful. You form new compound as products, must be A, D, plus A, and the minus D combined, and the C and the B. C is going to be on the left, B is at anion on the right. So A, D, or C, B. Now in the first case, we talk about either form a solid ionic compound. So if we consider AD is a new product, it is also ionic compound binary, and then we put S in the parenthesis for physical state, and the point down arrow means it precipitates, because why? The solid, just like the silver here, the solid is heavier, right? In the aqueous solution, the water-based solution, they cannot afloat, right? They are so heavy, they are dense, they go into the bottom of the beaker and they precipitate out of the solution. Now you say, okay, it's still in the solution. Well, it is still in the solution, but do you see the boundary between the solid powder? It precipitates down the bottom, and on top of the powdery, solid, metal particles is the solution, right? The solvent, the solution, with other cation-anion pairs, the solution, right? But they are no longer going back to the solution to go backwards. This is going to be what? Single direction, irreversible reaction again. Now this is what we introduced very early, like part 16. We review the generalized chemical reaction equation, right? How many? 5 or 6 different major points, major concepts we have to apply, and constantly keep in mind those major concepts, and then writing correct chemical reaction equation, right? So in this case, it's irreversible, so go one direction, and the solid precipitate, C and B become aqueous solution, stay in the solution, right? And how can we retrieve them? Yes, we can. We can filtrate the AD out of the solution with a filter paper, with a funnel. And then we have the aqueous solution with CV, right? So it is still cation-anion, zippings of cation C and anion B, right? In the solution, they are submerged in the sea of water, right? Water solvent. Then you evaporate, heat up solution. Let the water go. Let the water go over 100 degrees Celsius. They boiling the water become vaporized out of the solution. Finally, dried off all the solvent. The leftover is a solute. What is that? That's a CB. All right. So that's one. So this is what's the driving force? The driving force is the solid formation. It's the driving force. This kind of reaction has a tendency in it spontaneously form solid. So produce solid is the driving force. And the second kind, we talk about either the solid, right, ionic compound, or molecular compound as liquid, or liquid water. In this case, so you have AD and CV again, but AD could be a ionic compound, and in a dissociation status, right? They are dissociated into cation and anion pair in the aqueous solution. So A and D, they are cation and anion, but they are not combined anymore. In the aqueous solution, they just whirl around and in the entire beaker of solution. And then the C and the B, it is not going to separate it, just like a water. Become maybe just form water. The water is what? Water is liquid, right? We don't call water a solution. We don't call water is solid. We call water is liquid. And it become ice, it becomes solid, right? So in the aqueous solution, there's a lot of water. Where did it come from? The water comes from solvent. Right now we produce what? This reaction produces more. Add into the original solvent. But they are the same, water. Yes, they are. They both in the liquid status as a physical state. But this liquid, this extra amount of water molecule is not from the solvent you made a solution, right? Before you mix them, right? Before the AD or CD, the 2 beaker of solution, you mix them and then have a reaction going on. If you don't mix them, there's no contact between these 2 aqueous solution in 2 beakers. Until you mix them, they have a close contact. Then they are able to react with each other, right? And then if you form products, then that's a reaction. If it's not forming products, like we said, it's going to be called what? It's just a chemical dissociation process, or called a chemical change. We don't call them a reaction because there's no products, right? So that's the case. Now in this case, the water come out, the extra water come from the reaction will be joining the majority of solvent water, become part of the solvent, but it's actually, you have to specify those water, of course we don't get them out, those water molecule actually coming from the reaction as one of the two products. It's water. Now what is the situation in this kind of reaction? The acid-base neutralization reaction. So in this column, say these two chemical reactions can be also classified as what? Precipitation, simplified PPT, precipitation, precipitated. The solid is heavy, it precipitated down to the bottom of the beaker under the solution. That's called a precipitation reaction. That's another classification name, or you call solid formation. Now these two, right? And then the second type, form a liquid, right? You say neutralization reaction. The acid base neutralize each other, right? Become neutral water, right? The typical products for neutralization reaction is salt and water. Water is liquid. So we are able to say either neutralization reaction or liquid formation reaction. Now that's generalized description so far. Now let's get some example, right? Let's get some example to show you how those reactions can be recognized and classified. All right, so let's erase the whole thing. All right, give some example. That's a 2, right? Double. All right, so example for 2. Right? All right. Now, example, I continue, right? Example 2, right? Example, right? Now, for the first one, for the solid, right? For the solid formation, right? Solid formation, or we call precipitation reaction, right? PPT, PPT, right? So, still using the same compound, silver nitrate. Silver nitrate, so let's say silver nitrate react with sodium chloride. Now what is that? If you know the naming, you should know what is this. Silver nitrate, we already introduced that last experiment, right? No, the example. So what is it? Silver is Ag, nitrate is NO3, right? And it is an aqueous solution because this compound is ionic. Alright, it's a strong electrolyte and it will dissociate in water-based aqueous solvent, becomes silver cation 1 plus and the nitrate anion 1 minus, right? But for for the oxidation state, this is +1, this is -1, right? Alright, then you react with, this is clear solution, alright? Another one's a saline solution, right? NaCl, everybody knows that. NaCl also is aqueous, right? Now this is a cation +1 and this anion -1, right? Now when you dissolve in water, which is water already play a role in this equation already because AQ means water is there, right? And then what happened is going to be a one-way reaction and not reversible but irreversible, because why? Because silver is one of the precious metal and the heavy metal in the transition metal group, right? Then silver will combine with chloride to form silver chloride, which is a very, very insoluble salt. It has a very small portion of this kind of binary iron compound will dissociate into the water solvent, become cation and anion pairs. Majority, 99.999%, I don't know exactly, 10 to minus 15 mole per mole or something, it stay in solid. So what happens, this become the first products, AgCl, as solid, precipitate down, and then, alright, becomes solid, and then another one is what? Another one is left over. The sodium nitrate becomes sodium nitrate as aqueous. Now, if it's aqueous, we understand, now it will be able to completely dissociate into sodium cation, 1+1 oxidation state, and then the -1 oxidation state or charge of a nitrate, well, oxidation state inside is +5 and -2, but outside is anion has a charge is 1-. So let's put it here. That's a 1-. This is the whole thing, right? Now, in this case, what is the product? The silver chloride, heavy, precipitate down to the bottom of solution, and you are able to filtrate it, get it, right? And it's a white color powder. That reaction is so fast. If you have a small test tube of silver nitrate, it's very expensive. Silver nitrate is very expensive chemicals, right? A little vial, about 10 grams, costs you about $200. Maybe not 10 grams, 5 grams or something, and costs you $200 now. And then, but it's cheap, right? Saline solution, the table salt. Both you can mix one into two test tubes, and then hold that test tube in your hand, like this test tube in your hand, and it was a silver nitrate, and get yourself an eyedropper or the pipette. We call pipette in chemical lab, and withdraw a little bit about this saline solution, and then drop 1 or 2 drops, just 1 drop, and you will see the moment that drop of NaCl aqueous solution go into the AgNO3 silver nitrate solution, immediately a white, cloudy, milky precipitate formed, and then the entire test tube of silver nitrate become cloudy, white, milky solution instead of a clear solution. And if you set that test tube on the test tube stand and come back tomorrow, you'll find the top is going to be the solution, the solvent, basically have a little bit sodium in there and the nitrate, right? But silver chloride will be precipitated down at the bottom of the tube, very small, and it's not that white. It's going to be look like a little purple and a gray color, white, mainly white with little bit tint of gray and purple, powdery, precipitate, and settle down at the bottom of the test tube. That is silver chloride. Okay. So in this case, let's see if there's anything. We already said this is classified as solid PPT, right? The PPT is solid formation. Does it have any electron being transferred to be considered as redox? Let's double check. Silver on the left, this is 1+. Here, still 1+, because this is 1-, right? Otherwise, check the chlorine is what? Halogen, right? Either -1 or +7, that's common, right? Silver, I said so many times, only have 1 oxidation state, is +1. So +1 -1 neutralized. The charge become a neutral compound, and then the silver doesn't change its oxidation state before and after. So there's no electron transfer from silver to anything else. Nitrate, on this side, nitrate is -1 or 1- for the whole thing, 1-, right? For the charge, for the And the other side also, and the sodium is what? Alkali metal, right? Alkali metal, everything in that family is +1. So sodium +1 end up stuff. So there's no oxidation state change involved in this reaction. So it is not a redox, right? So it is the PPT, right? As a precipitate or solid formation. But, right? Let me do this. Not a redox reaction. Let me use shorthand in the future. RXN stands for reaction safe at the time. All right, not a redox because there's no redox transfer. So that's a one. Now then we have another example for what? For the liquid, right? Liquid formation. So let's say the acid, right? Acid. Let's put this simple reaction, right? Let's see. Hydrochloric acid, right? React with our sodium hydroxide, right? So that kind of reaction, the base, which is the base. Acid and base, right? It's a neutralization reaction. So what is hydrochloric acid? Hydrochloric acid, HCl, and it's not concentrated. It's going to be diluted in the water solvent, so become aqueous solution, and then react with sodium hydroxide, right? Sodium hydroxide. It's called a caustic soda. It's a strong base. And now, what happened? The double displacement, right? Here, double displacement what? The silver, right, took the anionic partner, right, of the sodium chloride and then to itself, and then released its original anionic partner to the sodium. So you have exchange of partner, then you form AgCl, and NaNO3. These are the double displacement. In this case, the same thing. If we exchange chloride with the hydroxide, and then you form a new compound. Let's see, what is this case? Now this is also caustic soda is soluble, and then strong electrolytes is a base, a strong base. This is strong acid, this is strong base. The common typical products of a acid-base neutralization reaction, right, is forming salt and water. So, and also it's a one-way irreversible reaction, one direction. So goes to what? So if you exchange partner, right, the Cl, right, the anion, going to what? Going to combine with the cation of sodium. In other words, sodium exchanges its own anionic partner OH, which is hydroxide, with the other reactants, its anionic partner chloride, and then the sodium combined with chloride, and the proton, which is a hydrogen, combined with a hydroxide to form two new compounds. What is that? NaCl is aqueous. Now because, and you know that we just talked about NaCl, same NaCl right here, all right? It's a sodium chloride is a strong electrolytes, what we call saline. It's aqueous saline solution in water, all right, solvent. And then it is going to be 100% dissociate, not first dissolve and dissociate into the solvent water, right? Become aqueous solution. And the cation, sodium is +1, right? alkali metal, first family in the periodic table. Chloride, the chlorine, right, belong to what? Belong to the halogen. It's -1 or +7. In this case, it cannot be +7 because you don't make this whole thing is a positive. This has to be zero, neutral, right? So it is a strong electrolyte and then is able to dissociate into the water solvent, become aqueous solution. That's what AQ stands for. That's what we call salt, right? Is that called salt? NaCl? Yes, salt. So that's a salt. And then plus 1H combined 1OH, what is that? H2O. Now this time is liquid. Now that is the products for no, water, liquid water, right? Liquid water. All right, liquid water. And is there any electron transfer? Let's double check. Hydrogen is +1 as oxidation state to start with, and the chlorine is -1, right? As reactant. Right, here's +1 for sodium, and the hydroxide what? Hydrogen is +1, oxygen is -2, so the whole thing is -1, +1, neutralized, neutral compound. But then, right? But then you go to here, the sodium still +1, chloride still -1, and water is what? It's +1 times 2, right? And here is what? -2. So that whole thing become neutral, right? So the oxygen is not -2 in hydroxide, and the oxygen is -2 in water. The same, right? It doesn't change at all. So there is no electron loss or gain between any of those components, right? Any of those components. So this reaction is not redox, but we call neutralization reaction. So not a redox reaction, but so liquid formation or acid base neutralization reaction. Alright, is that clear? Now that is the two simple example for double displacement reaction, right? Now we're gonna have more and in the homework, and as well as if you read textbook, you will have some more if you have time, right? We can give you more. Oh, read my handout, right? My handout have those examples in there, right? So we got a minute, and then we introduce the third kind, right? That's the second kind. And the third kind. Third kind is going to what? Third kind is going to be, right? The kind we call what? We call combustion reaction. Let's use this. Combustion reaction. What is the definition for combustion reaction? Right? Most of the case, it's defined as organic compound as a fuel and organic compound and then burned in the air which contain 21% of volume of oxygen and then produce typically two typical products. One is carbon dioxide, the other one is water vapor. Now this time is H2O, but it's no longer liquid. It's water vapor. Now, but this whole reaction, for instance, we burn organic compound in gas phase, for instance, methane, natural gas, right? That is the gas burning oxygen in the air, also gas, to produce carbon dioxide as gas, right? That's greenhouse gas. So times up, and then but the water is also gas. We do not carbon gas formation. So gas is not gas formation reaction. Now time's up. That will be the next part of the part 22.